一天吗？天数，是的。现在对，就是可以投配上。对啊，那这种把品牌的不对，少还是不对。就是说他们之间可以等一个。哦。嗯，如果有等于的话，就有一些 contradiction。多了，两种，因为他们封就 sub 不久了，都 close 了，都 close 了吗？不会再多了，你这个 portfolio 就不会再多了，多的都给你。Hello, testing. Okay, good morning to everyone. So, this few days I got stiff neck, so I can't move much. 落枕，所以我不能够动作太大。OK，所以可能有点慢。OK，I'll be very slow. I can't move my neck. Yeah. So here's the Feynman learning method for you to refer. So in my class, I always ask you to ask why. Okay. So please ask why. Don't just follow what people did. Ask why. Okay. And getting more and more people come to my office hour. But I believe have you seen my assignment feedback yet? Yeah. So I posted out the solution. Maybe when people get more, then we can discuss later. Okay. And then yeah, maybe we'll talk about assignment later. So how about we decide what kind of replacement time you have? Because in November, December, we have 3 of Monday holidays. So my prefer is to not to do 3 days, but maybe we do 2 days for 3 hours. Okay, so that we don't need to come so many times. Okay, so you let me know now. You check your timetable. When do you have 3 hours slot? Huh? Sorry? Yeah, Friday, Monday afternoon. Okay, after 2, Monday afternoon after 2, after 11. Okay, you cannot. You 2 to when? For your class. Okay, so maybe Monday doesn't work. Friday. Okay, Friday. Friday morning, afternoon. Okay, Friday afternoon after 2. Okay, yeah, so maybe we'll do 2 to 5 for 2 weeks on Friday. Oh, that then we only use 2 hours. Friday. Can we start at 1? Why not? Friday. Or LLM. Huh? No more other than Tuesday, Wednesday, Thursday. Cool. Then, then Wednesday one time. Morning, afternoon. Afternoon I got class. Afternoon my class until 6. No more. Huh? No. Huh? Then what? What do you mean? 这样2小时变3小时。For this class, we can extend early 1 hour, but because remember people will come in after our class.
So you mean 7 a.m. viewers?
No, today is 8. Today is 9. Today is 9. And then on Wednesday, people also coming in. Yeah, after. Maybe if Wednesday extend 2 more hours, I look for classroom. Is it okay or not? If 1 more hour, I think no point to do that. We run there, then we sit for a while, then we go. Yeah. How about like that? Huh?
It's crazy.
Huh? Otherwise, we need to do Friday for 3 weeks. Because people only free from 2 to 4. Three weeks of Friday. So in that case, maybe we just change the Friday 3 weeks become Friday 3 weeks. Then the usual usual Monday class on that week change to a Friday class. That's
fine.
Okay.
Perfect.
Okay. All right. Yeah. Okay. So for the week you have holidays. Okay. For 3 weeks Monday we change to a Friday 2 to 4 class. That's all. Okay. Yeah. Yeah. For the week you have holiday. Awesome. Yeah. Okay.
What's your class?
6 hours.
Okay lah, yeah. The weekend hours, 8 hours.
So how? Huh? 3 to 5. Friday 3 to 5. How about Friday 3 to 5? Oh, they got computer lab. Flash. Saturday. Okay. How about 4 to 5 you come to my class and then 5 to 6 you go to the
But you need to ask the truth.
Jinsen? Where is Jinsen? Okay. And maybe let your lecturer know. If the lecturer can. Okay. Yeah, so email him at first, like before you say. Yeah. Okay. Okay, so maybe we fix Friday 2 to 4 first. Okay. If really you guys cannot, then can watch the recording. Hey, but how about the LA is 3 to 5, huh? So 3 to 5, 2 to 4, 3 to 5, 3 to 5. Okay, 3 to 5. Okay, so Friday 3 to 5, huh? Okay. Okay. Oh, no. Is Ginseng coming or not? Don't know. Maybe I discuss assignment next hour. Okay. So let's start the course first. Okay. Where did we stop last week? So last week we stopped at the isomorphism. Okay. So we have a map between groups. Okay. How is it a homomorphism? That satisfy one property, which is what is the property? Multiplicative property. Okay. So for all A and B in your domain, okay, phi of A B equals to phi A times phi B. Okay. So this is a homomorphism. So how is it the isomorphism? Okay, isomorphism is a homomorphism that is bijective. Okay, 1 to 1 and 1 to. Okay, so let's do one example. Okay, so I'll prove that the group generated by 1, 2 is isomorphic to the group generated by 2, 3. Okay, Let's try one example, how we construct an isomorphism. Okay, how we construct an isomorphism. So first of all, do you know what's the group generated by 1, 2? What is in the group generated by 1, 2? What's the group generated by 1, 2? Letien. Don't know. What is 1, 2? Where does 1, 2 live? Sonic, where does 1, 2 live? P. What's P? Yeah, permutation group. Okay. So live in X2. Okay. So permutation of 2 indexes. How about 2, 3? Where does 2, 3 live? Right? Huh? Also in S2? So when I put 3, right? There's 1, 2, 3. So like I'm trying to permute 3 things at least. Okay. So this is living in X3. Okay. Of course, you could say 1, 2 live in X4, X5, F6 because more than n 2 and the 6 you contain 1 and 2, right? But this is the smallest permutation that contains them. Does it make sense? Smallest permutation group that contain them. Okay. So it doesn't make sense to write 2, 3 in S2. Okay. Because if you just want to permute 2 and 3, just relabel them. Okay, relabel them to 1, 2. That's all. So when I put 2, 3, meaning I want it to live in a permutation set of 3 elements. Okay. So Letian, do you know what's the group generated by 1, 2? Cycle 1, 2. Okay. So to satisfy subgroup, right? What property you need to satisfy? 3 properties. What? Venus. What are the properties of subgroup? Yes. Identity need to exist, and then inverses for every element. One more. Associativity. Not quite. Subset, sure. Okay, and then more. Sorry? Yeah, subgroup. When you compose, it has to be close. Okay, so you need to stay inside. So you need to take the closure of this element here. Okay, so meaning 1, 2 times 1, 2 have to be in the subgroup. Okay. So first of all, 1, 2 have to be in the subgroup. So what is transposition? Square. 1, 2, you permute, and then you permute 1, 2 again. What do you get? Identity. Okay. So you can check that these are all the elements in this group. Okay. Because 1, 2 is a inverse of itself. Okay, so inverse exists, identity exists, and then it is closed under multiplication. Okay. Okay or not? Okay, how about group generated by 2, 3? 这样的, what do you have? 2, 3. Okay, first of all, you have 2, 3. Anything else? That all? You need to satisfy closure. Okay, so meaning 1, 2 times 2, 3 times, sorry, 1, 2, 3 times 2, 3 need to be in the group. What is 2, 3 times 2, 3? Huh? Identity. Okay, so to satisfy closure, identity have to be in the group. Or not? Okay. Then you need to consider all the combination again. 2, 3 times identity. Identity times 2, 3. Identity times identity. Okay. So you need to check all combination. Okay. So is it close under all the combination or not? All the products. Okay. So if it's closed, then this is all the elements in your group. Okay. Does all of them has inverses or not? 2, 3 is the inverse of itself. Okay. Identity is the inverse of itself. Okay. And then identity exists. Okay. So you want to prove isomorphism between two groups. Okay. Isomorphism is what? So we want to define isomorphism B, okay, between two groups. Okay. So in particular, morphism is a map. Okay. So if it is a map, you need to tell me where each element send to. Okay. So on the right, I have identity and 1, 2. Sorry, on the left. And then on the right, I have identity and 2, 3. Okay. So who have to send to which one? Why? Identity have to send to where? Yeah, right. Because group homomorphism. Okay. If you don't do that, you might not get a group homomorphism. So if identity have to go to identity, in this case it's easy. Then the leftover have to be sent to the other leftover. Okay. So this is a map. Okay. So I claim that this is a homomorphism. Okay, homomorphism. So we need to check. Okay, so first claim is a homomorphism. Okay, so for homomorphism, what do you need to check? Jimbo. What do you need to check for homomorphism? What equal to phi A and phi B? Phi AB equals to phi A times phi B. This is true for what kind of AB? AB in the domain. Okay, for all, so you need to check all A and B in the domain, which is 1, 2. A B equals to phi A times phi B. Okay, so you have left hand side, you have right hand side to compute, then they have to be equal. Okay, they have to be equal. So what kind of combination you have on the domain? So what kind of AB combination you have? 1, 2 times Z, and then E times 1, 2, 1, 2 times 1, 2, E times Z. Okay, so you really need to check every AB. Okay, really need to check every AB. So I apply phi on all of them. Okay. And on the right hand side, what do I have? I have phi of 1, 2 times phi of E. And then phi of E, phi of 1, 2, and then phi of 1, 2, phi of 1, 2. Okay, maybe I reduce the bracket faster a little bit. Okay, so we want to show that they are actually equal. Okay, they have to be equal. Okay, so we do it step by step. So first, phi of 1, 2, E equals to phi of 1, 2. Okay, phi of E 1, 2 equals to phi of 1, 2. Phi of 1, 2, 1, 2 equals to phi of E. Phi of E times E equals to phi E. Okay, so this is the reason why we define the map on every element. Okay, so that we know what happened to all the elements after applying the map. Okay, so where does phi 1, 2 get sent to? 2, 3. Okay, let me ask Xianmei, where does phi 1, 2 get sent to? 2, 3. Where does phi E get sent to? Ellie. Where does identity get sent to? Don't know. Identity. Identity must go to identity. Okay. Okay. How about the right hand side? Okay. How about the right hand side? You kind of see what is going on already. Okay. Before we get that, they are the same. What's the difference here? So we have to evaluate phi 1, 2, and phi separately. Okay. So phi 1, 2 is 2, 3. And then phi E is times E. Phi E is E. Phi 1, 2 is 2, 3. And then phi 1, 2 is 2, 3. And then you take the product of itself. And then phi E times E is E times E. So why does the yellow equation hold? Yeah, it holds. So why? Because these are the equalities in your codomain. Okay, because these fall in the group of your codomain. Okay. Okay. Did you see what's going on here? Okay. Any question? Okay, so when I say for all, right, you really need to check for all. Okay, for all kind of combination. So we got the second claim is phi is and bijective. Okay, phi is bijective. I would say that this is clear for construction. Can you see why? This is clear from construction here. Show bijective, what properties you need to show? 1 to 1 and on 2. Okay, so first of all, is this a 1 to 1 map? Why? Get sent to different element. Okay, but we have a proposition in our class saying that a homomorphism is injective if and only if the kernel is only the identity. Okay, so there's only identity gets sent to identity here. Okay, so let me write down. So phi is injective since kernel of phi equals to the identity. Okay, how about 1 to 1? Sorry, how about on 2? Why is it subjective? Yeah. Okay, so for every element in the codomain, okay, you have a pre-image. Since for this is a definition for every element in the group generated by 2, 3. Okay, there's this X in for every element Y in the group generated by 2, 3, there's an element in 1, 2, such that P of X equals to Y. Okay, so how do you show this statement here? For every Y in 2, 3, there's an X in 1, 2, such that Phi X equals to Y. How do you show this element? How do you show this statement? How do you show this statement? This statement is true for all Y. Okay, so how do you show this statement? So you need to check for, you literally to check for all element in your codomain. Okay, say I give you Y equals to E. Who is the pre-image? E. Okay, I give you 2, 3 in the codomain. Who is the pre-image? 1, 2. Okay, so you need to produce like this. Is that okay? Yeah, question.
So,
okay,
can we just draw the mapping?
Yes. Yeah, so that's why I said these two properties are clear from this construction here. Complicated case, either you have a way to describe how you send element in general, or you really need to do this brute force. Yeah. Either you have a general way to tell how you send your element, or you really need to say one by one. Okay. So yeah, so this is kind of tedious. Okay, so this is kind of tedious. So that's why we care about basis. We care about generator. Okay, because once you have a basis for vector space, how do you tell map between linear transformation, linear spaces? You don't need to tell me how every element go, because there are infinitely many of them. How are you going to tell all of them where they go? Okay, so you just tell me where the basis go. Okay, since all the element can be expressed in terms of basis element, then I can know where the rest go. So this will be similar to this group case. Okay, later on we will learn generators and relation. Okay, so we just care about generators. Why? Because remember, homomorphism is a multiplicative property. Okay, so if I can break all the elements in my group into generators, then I will know how they get sent to the image. Okay, clear? Okay, yeah. Later we will learn about generator. So in this case here, so for example, in this case here, this is generated by 1, 2, and 2, 3. So in principle, I just need to tell you where my generator go is enough. And then E to E is implied already. You believe me or? Let's say I said, you see, there's really only one generator on each side. Where can you send to? You cannot send to other pairs already. 1, 2 have to go to 2, 3. Okay. Does this imply E have to go to E or not? See here. If I just define for 1, 2, and I just define for 1, 2, I must get phi E equals to E. Okay, to get the homomorphism. So meaning these you don't need to compute actually. Okay. Yeah, question? Any question? Okay, so in the assignment, I asked you to show there's no isomorphism, right? Okay, so how to show something there's no isomorphism? You probably need to start with a contradiction. Okay, suppose there's one, and then try and find contradiction. Okay, Yeah. So one example you can try and do a little bit more advanced, a bit not advanced, I mean a bit more harder, a little bit harder. So try and show that the group generated by 1, 2, 1, 2, 3 is the same as 3 and 3, 4, for example. Again, try and work this out. See, you really understand what is checking the property of group homomorphism. Okay? Try and work this out yourself. Okay. Yeah. So this is actually the group S3. Right? Yeah. So I want you to have an idea of what is a group isomorphism doing. Okay. So this is what we are doing here, what we are checking here. Okay. What is the property we need the isomorphism to hold? Okay. Okay. So I want to bring back. Okay. So let me bring back the multiplicative table that we worked out last time. So remember where the we stopped last time? So we stopped at the Cayley theorem. Okay, what does the Cayley's theorem says? So every finite group is isomorphic to a subgroup or permutation. Okay, or Sn. Sn. Okay. So every finite group is isomorphic to a subgroup of Xn. So one thing I want you to observe here. Okay, let's observe here. So I think historically this multiplicative table is also called a Cayley table. Cayley table. So these are called the Cayley table. So let's look at one example first. So let's look at Z4. Okay. Did you see any repetitive of element across row or column or not? Try and see. Any terms like 0, 1, 1, 0 like that, or 0, 2, 2. Did you ever notice this? Why each row and column there's no repeated elements? Okay, so this is not just true for Z4. This is also true for all these groups. So like Z3 and then Z2 cross Z2. Okay, you can see that across the row or columns, okay, there's no repeated elements here. Okay, so this should spark you to the group 2 of permutation, right? Okay, so why is it true? Why is it true in general? Let's say if I replace, okay, let's say in the Z2 cross Z2 case, if I replace C here, would there be a problem or not? So let me use. If I replace as C, would there be any problem or not here? There be any problem? This means what? E times B equals to C. E times C equals to C. Is there any problem here? This means EB equals to EC, which means B equals to C. So this means you don't need two lines. You can collapse one of them if I repeat. Okay, so they really have to be different. Okay, in each row or each column. Otherwise, you can collapse the group. Okay, so this is a general statement. Okay, so this is true for general. Okay, so how we describe this this phenomenon here? So let's define something. Okay, so let's define something. So I'm starting the proof now. So let's define the left. So define the left regular representation G to be the map lambda x, okay, that sends every element in G to x times G. Okay. Okay. So what am I doing here? I look at a fixed x, okay, I'll multiply to every G. Okay. So in the language of this multiplicative tables here, what do? I take elements in G, okay, I fix one of them, and then I multiply on the right. Okay. So if I study this map here, this is equivalent to study the row of my multiplicative table. Does it make sense? Okay. I got an x, fix an x, I multiply G on the left. Okay. For example, E times E, E times A, E times B, E times C. Okay. So this is a lambda. This is a lambda. So this row is given by lambda E. Okay. How about second row? Second row is given by lambda what? Lambda A. Okay. So this is given by lambda A. How about the third row? Third row is given by lambda B. Okay. And then the fourth row is given by lambda C. Okay. Does it make sense now? Okay. So we try to study this table here. Okay. Using this lambda. And this is not a coincidence why we say this is a representation. So representation theory, the definition of representation is close to this definition here. Okay. So this is a map from where to where actually. So let me down. So I only tells you how to send element, right? So this map is really going from, can you guess where's the domain and codomain of this map? Where do I get my G from? Little g. G, okay, the big G group. And then I multiply by x, I still live in G because my G is close. Okay. So lambda x is a group from, is a map from G to G. Okay, where I send little g to SG. Okay, so that's why I label my x with a subscript x here. Okay, so this is really dependent on what x I look at. Yeah. So just now said there's no repetitive. So meaning this lambda x is a permutation. Okay. So to prove something is a permutation, what do you need to show? How to show something is a permutation? What's the definition of permutation? Huh? Right. So how do you define rearrange? What's the definition of permutation? So you use arrangement to define arrangement. So what's the definition of permutation? It's a map. What kind of map? Bijective? That's all. All bijective maps are permutation. Okay, bijective map. Okay, again, 1-to-1 and onto. Okay, so we need to show it is 1-to-1 and onto. So this is a bijective map, by the way. So this is just a fancy word for bijective map. So permutation, you really is a bijective map. Okay, 1 to 1 and on 2. So I need to show 1 to 1 and on 2. Okay, so how to show 1 to 1 and on 2? You need to show from the definition. Again, we'll repeat a lot 1 to 1 on 2, 1 to 1 and 2 in this class. Okay, so 1 to 1. So how to show 1 to 1? So you want to show that if lambda x on y equals to lambda x on z, then y equals to z. Okay, is it everyone clear about this? 1 to 1 is if phi y, if phi is 1 to 1, that means phi y equals to phi z equals, then y equals to z. Okay, if the image is the same, then the pre-image must be the same. Okay, 1 to 1. So suppose in this case we suppose lambda x y equals to lambda x z. This implies what? This implies that xy equals to xz. Okay, by definition of lambda. Okay, so what does lambda did to y? Multiply left by x. Okay, similarly, lambda x on z is multiply x on the left of z. Oh, yeah, right. Okay, xy equal to xz, and then can you deduce y equal to z or not here? How? Okay, so inverse of x as is, you can multiply x on both sides. In particular, this is what law? By the cancellation law. So by the cancellation law, y equals to z. Okay. How about on 2? On 2 meaning if for every g in G, okay, there exists a g prime in G such that lambda x of g prime equals to g, right? So for every element in the codomain, I can find a pre-match. Okay. So if I give you a G in the domain, codomain, what kind of a G prime you can pick for me? Michelle. What kind of G prime you can pick? Okay, such that phi of G prime, okay, lambda of G prime equals to G. Or in other words, x times G prime equals to G. So what's the G prime you need to pick, Michelle? What's the G prime you need to pick such that when you multiply left by x, you get G? Any idea? No idea. Ling Jing, any idea? What's the G prime you need to pick such that when you multiply left by x, you get G? Any idea? This is really a very short thinking. Okay, you cannot spend too long. If this spend too long, then it's quite hard for you. Okay. Tanya. Yeah. Okay, you just pick x inverse G. Okay, so x times x inverse G. Okay, x times x inverse is identity. Identity times G is G. Okay, so you got G. Okay or not? This is not something very hard one. Okay, so just need to be a little bit. We say Chinese say 活一点. Okay, creative a bit. Okay, 要灵活 creative. Yeah, flexibility. Okay. Yeah, good. So we show that these are all permutation already, right? Okay, so we show that this is permutation. So what's the thing we're gonna do here? So recall what we want to show again. Yeah, recall what we want to show. So we want to show that So we want to show that a finite group is isomorphic to a subgroup of Sn. Okay. Subgroup of Sn. So meaning we need to construct a map. Remember, isomorphism is a map, is a homomorphism, which is 1 to 1 and 1 to 2. Okay, so we want to construct a map. So what's the map here? Okay, let's say we have a G. Okay, we want to map into some Sn, some subgroup. So what's the map we're considering here? So to tell me a map, right? You need to tell me all the elements where they get sent to. Okay. So for all the x in G, where should I send the x to? In particular, the codomain here, what are the elements? The elements are the permutation. Okay. So for a group element, how you produce a permutation? I just proved it. From a group element, how you produce a permutation? I just proved. What is permutation just now? Yeah, sure. So I mean, what did I prove just now? What's the segment I proved 5 minutes ago? Definition, not strong enough. Definition. I just defined one thing you already forgot after 5 hours. So you imagine how you can stand for 2 hours class. I only define one thing in 5 minutes only. You already forgot already. Or you don't know actually. So how you gonna withstand in 2 hours class, math class? You will cry. You know? What's the one thing I defined just now? I don't want to recall. What's the, yeah, okay, that's the map I defined. So what is it called? It is not an isomorphism. What's the name of the lambda x? What's the name? Left regular representation. Okay, this is the only thing I defined just now. Okay, left regular representation. Okay, so I have an element x. I can define a left regular representation, lambda x. I prove that it is a permutation. Okay, so in particular, it's an element in Xn. Okay, so I can send every element X to the left regular representation. So what's the n you need to consider here? How many n are you permuting? How many n are you permuting for the left regular representation? Lambda x permute how many elements? Yes, the cardinality of G. Okay, so it permutes the cardinality of G. Okay, so actually I produce a map to X of cardinality of G. Okay, so we produce a map here. So let's define the map phi. Okay, phi going from G to H, lambda X to lambda X. So phi sends X to lambda X. So to show that it's isomorphic to a subgroup, what do we need to check here? We need to check what? So we need to check that. So the proof strategy. What do we need to do? So the first thing we need to do is we really define a homomorphism. We need to do a check on homomorphism. Once we check that it is a homomorphism, image of a homomorphism of a group under the homomorphism is still a subgroup. group. Okay, it's a subgroup of the codomain. Okay, then it follows P of G is a subgroup. Okay, in your codomain. Okay, so this is by theorem. Okay, this is by theorem last time. Remember, we spent 1 hour to prove this. Yeah. Image of a group under a homomorphism is still a subgroup. Okay, in the codomain. Okay, after this, what do we need to show? We need to show that phi is 1 to 1 and onto. Okay, so that P of G is so that what? So that G is isomorphic to the subgroup in X of G. Okay, it's not necessarily equal to the XG. Okay, XG sometimes is too big. Okay, but it just equals to some subgroup. We cannot show surjective onto the whole XG. Okay, or onto the whole Sn. But you remember, every map is surjective onto its image. Okay, every map is surjective onto its image. Okay, so for example, I want to correct your concept. So let's say I have an arbitrary map. Okay, from phi from G to G prime. Okay, so I have a map from G to G prime like this. Can you produce me a surjective map or not? Let's say the image of H is H. Image of G is H. Can you produce me a surjective map from here? In G. How can you produce me a surjective map? Sorry? Yeah, can you speak louder? Can you produce a surjective map? Yes or no? No. Yes. I want to say yes. You can produce a surjective map. How to produce a surjective map? Just throw away all the things that doesn't map by phi. Okay, then this is a surjective map. Right? What's the definition of image? It is mapped by some group in the mapped by some element in the domain. Okay. So in particular, the pre-image is non-empty. Okay, so this is onto. So for every element in your codomain, the pre-image is non-empty. Okay, it's onto. Okay or not? Okay. Yeah. Okay. So let's do it. Okay. So how is it a homomorphism? So let's prove the first one. So Y P is a homomorphism. So what do we need to show? So we take xy in G. Okay. We want to show what? Lambda xy equals to lambda x times lambda y. Okay. I claim that this is obvious. Okay. It's not I'm arrogant because it's obvious. Okay. So why is it obvious? So this is an equality of what? Equality of number, of set, of function. Which one? This is an equality of function. Okay, so how to check equality of function? You need to check on every group element. Okay, you need to check on every group element. Okay, so take G. So what is x lambda x on G? This is just xy times G. How about the right hand side? Lambda x times lambda y apply on G. What do you get? You get lambda x on y times G equals to x times y times G. Are they equal or not? Grace. Are they equal? Why? Why? Why are these two equal? Yes, associative law of group. Okay, so they are equal because it's LOC. The LOC of G is associative. Okay, so you see, property of group comes in already. Okay, property of group comes in. We need to use it. So we already show that this is a homomorphism. How about 1-to-1? We want to show that B is 1-to-1. So phi is 1-to-1. What does it mean? So since this is a group homomorphism, right? Okay. What's the way we can show 1-to-1? Phi is injective if and only if the kernel of phi is only the identity. Okay. So kernel of phi equals to identity is the equality of set of function of number or what? It's the equality of set. So you need the inclusion. Okay, two inclusion here. So if and only if, so we only need one direction. Okay, we only need one direction. Correct or not? So if the kernel of phi is E, then phi is injective. Okay, we need to prove that. So that means we want to show kernel of phi is actually identity. Okay. So one inclusion is easy. Which one is easy? Left to right or right to left? Which one is obvious? From the include from where? Which inclusion is easy? E contained in the kernel. Why? Why is this easy? Lambda of E is what? Lambda of E is the map that sends everything in G to G. In particular, lambda E is the identity permutation. Okay. So identity permutation, is it identity of permutation or identity element in permutation group? Right? So phi, so our phi sends E to lambda E. So this is the E is the identity in G. Lambda E is the identity in X G. Okay. So identity is in the kernel of phi. Okay. Clear? What is the kernel? Still remember what's the kernel? Kernel is inside a nut. Then you send kernel to identity. Okay. Everyone okay? Okay. So how about the other direction? How about the other direction? The other direction means what? If your map is the identity map, okay, if your image is the identity map, then your pre-image must be a identity. Correct or not? Correct or not? Do you think it's correct? If you have an identity permutation, then it must be met by an identity element. Can you convince yourself or not? I know mathematician is quite stubborn one. Alright, it's quite stubborn. So how to deal with this stubbornness? So suppose, okay, suppose there's other thing, okay, in kernel of phi, okay, which is not equal to the identity. Well, let's say we have some element in the group which is not identity, but phi of x equals to lambda of identity. Okay, but what is phi of x in our case? Lambda x. Okay. Is it clear now? Is it clear here? Okay. Okay. So we want to derive a contradiction. Where to derive this contradiction? Where's the contradiction here? Then the contradiction already appear already. So where's the contradiction? Lambda x equals to lambda e, but x is not equal to e. Where's the contradiction? This is the equality of what? Function. Okay. Are they equal as function or not? Where does it not equal? Tell me. Sure. You can throw in the elements, but can you find an obvious way to see what is false? Huh? Yeah, 1-to-1. We want to prove 1-to-1. Cannot assume 1-to-1. Cannot assume result. Okay, so what's the obvious point to see they are not equal? Apply to what? Apply on? Apply to what? Apply to E. Huh? Not that they are equal. This means what? X times E equals to E times E. Which means what? X equals to E. Any contradiction or not? Where is the contradiction? Suppose X is not E. Okay. Okay. Okay or not? Okay. So you have to be very clear what you are supposing. Okay. Very clear about the definition. Okay. So I think I understand why sometimes you get confused in my class. Because sometimes I hold onto the definition quite fast because I keep seeing this definition for a long time already. And last Friday I joined a seminar. I haven't studied already. Study with the other people. So I also confused. I was in the same situation as you. Why am I confused? Because I'm not good with the definition. Okay. So make sure before you come to the class, do some pre-reads first. Okay. Get familiar with the terms. Okay. Terms is very important. And then what does it mean by that terms? Okay. For example, just now, within 5 minutes, I only give you one definition. You cannot remember. You cannot remember. Definition is very important. When I say I define left regular representation, this word you need to register inside your mind already. Register inside your dictionary. Left regular representation. Okay. And then what is left regular representation? Is a map? Is a set or what? Okay, it's a map. Okay, what's the map? Is the map that sends x to lambda. It's the map that sends x to xg. Okay, I call it a lambda x. Okay. So doing step by step. Okay, so you need to start somewhere. Okay, so wait. So s equals g, but which is a
Okay. Yeah. So how to show onto? We cannot show onto on XG. Okay, we cannot show. So this means what? This means 3. Phi is only onto its image. Okay, onto its image. But this is enough already. This is enough. Okay. What is the image? Image is phi on G. Phi on G, last time we proved homomorphism of a group. Okay. The image of a group under homomorphism is always a subgroup inside your codomain. That's all I need. So this is a subgroup, which is a subgroup. Subgroup on X of G. Okay. 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 So this is still not the hard proof. This is about level 2 only. Okay, level 1 is you don't need to construct much thing, but this one you need to construct a little bit thing. But for the definition of hard proof for me is you need to construct things out of nowhere. Okay, you need this still okay a bit. Okay. And a lot of analysis proof you construct out of nowhere. You just construct one function that works, and it works. That's all. That's all I want. Okay. Yeah, this is a remark. Either I will mention later or we will skip it. I will keep it in the lecture notes. Okay, so let's break for 10 minutes and then we come back at 10:18. 10:18. If you have questions, leave to next section and then we will answer. Okay.
我看一下那个 regular representation，刚刚那个 definition 太快了，我没有注意看。
Okay.
非常避免。所以如果OK 我明白了。所以如果你，所以这个到时候就是你的 representation theory 一直在做的东西。
represent
一个 map。
我们的 map 是从 G 到 GLN， 所以我们没有回去我们回去那个 general linear， 对，我们 act 在我们
可是你到时候也是一样，不会去弄完整个 GLN， 反弄一个 subgroup of GLN。
就是 depend on 我的 group 如果是 representation of group 如果也有 representation of algebra 就 depend
representation of algebra。
就是你把 algebra map 去一个 general linear group 也是一个 algebra。
algebra 是那种
as in algebra 的 as in 就是 algebra 的意思就是说像 matrix 你可以加你可以乘。group 的话你是看
这个有 right
有
啊
right。
呀，
如果你 right 的话，是什么情况？你是看他的看他的 column。呀，你可以用 right。你这个 proof 整个可以 replace 成 right。
可是我们上面有差，因为我们就是 G to G 嘛，G 要 N 才 left 跟 right 才有差，还是
有差，
这边有
差，诶，有差，你看，诶，有差吗？OK，这个 group
哦
abelian，这个 group 这两个 group abelian，所以你看不到差别。你要去找一个不 abelian 的 group，你会看到差别。
哦，因为它不 commute 啊，对。
耶，它不 commute，对。但是重点就是说，他们是一个 computation。
我放一个 identity 非常这边。
没有诶，你里面好像是错的哦。
第三个啥？
我知道，可是你后面好像是错的。你看啊，1去4哦，这样它就卡在这里哦。呀，这你看，1去4，1先去4，可是我1是去2。呀，你怎样 get 到那个东西？我不知道。你怎样 get？try 了，你就 try 吧，
都会可能，应该是
try 吧。
那个 Alex
对，是 Alex 哦。
Alex 就是
哦，那个 Alex 了哈，知道。
没有来
原来。
啊。
In the meantime, we will take some attendance. Venus 乐天伟泽三快乐啊三严科应该联系泽瑞 OK Raylan not here. You know where's Raylan? OK 至于金生顺灵林也凯仁金波华英一雄英奇何怡雪岩嘉业。Hey, Jaya, why are you not here last week? Okay. Think he didn't call you to wake up? 李凯 Okay. Huh? What? Oh, 严家文硕一定誉为燕博本业呀林金董洁OK 一周呀定宇柳晴 OK 真诚呀说宁说宁 what happened to you last week? Okay. Yeah. When didn't start, then go back to sleep. 鼓励 Wise Wise 子谦子谦 OK 莹莹 not here. No. Grace yeah. Sayek Michelle Ryan Ellie 沈梅子源 I think 子源 here is 子源 maybe I call again
语言。
Okay, let's start. Okay, so I quickly give you an example to this theorem, right? So this theorem is so big, so I must find an example. So for example, we look at Z6, okay? So the claim is Z6 is isomorphic to a group which is in XG, okay? So SG is X what in this case? How many elements in G? 6. 6, right? Okay, X6. Okay, but this hash here, you can pick it to be the disjoint cycle 1, 2, 3 times 4, 5. Okay, so what do I mean by isomorphism here? Okay, they both must have similar structure. On the right hand side, Z6 is generated by how many elements? Why? Generated by how many elements? Z6. Too many. Z6 is generated by how many elements? What's the group Z6? Z6 is what? What kind of group? Is an abelian group. It's also a cyclic group. Okay, what does it mean by cyclic group? Can be generated by one element. So what's the one element here? 1. Okay, you just use 1 to generate everything. Okay. In particular, integer is also a cyclic group. Okay. Integer is also a cyclic group. How you define 2? 1 plus 1. How you define 3? No, you define as 2 plus 1. So what is 2 plus 1? 1 plus 1 plus 1. So everything defined by 1. This is P&O axiom. Okay, P&O axiom. Okay, so this means that my hash is also generated by one element. Okay, let's see why is this true. Okay, so first element you must have is 1, 2, 3, 4, 5 in this case. So let's list down what happened in Z6. So you have 1, 1 plus 1 you have 2. 2 plus 1 you have 3. 3 plus 1 you have 4. 4 plus 1 you have 5. 5 plus 1 you have 6, which is just 0 in this case. Okay. So similar, you should see similar structure on H because this is an isomorphism. Okay, so their structure should be preserved. So 1, 2, 3, 4, 5. Okay, let's say 1, 2, 3, 4, 5. What are the next element you should have? You take 1, 2, 3, 4, 5. Similar as 1 plus 1. You multiply itself. Multiply with itself. What do you get? 1, 1, 1. Calculation slow. 1, 3, 2. Good. Okay. And then the next one. 1, 3, 2. What do you want to do for the next? You can take 1, 3, 2 times 1, 2, 3, 4, 5. What do you get? You get 4, 5. Okay, you get 4, 5. You get 4, 5. Okay, and then 1, 2, 3, 4, 5 times 4, 5, you get 1, 2, 3. Okay, and then 1, 2, 3. What's the next thing we want to do? 1, 2, 3 times just 1, 2, 3 times 4, 5. Does it work? Does it work? It's a new element, right? Okay. And then what do you have? Do you have identity here? Who multiplies with who will get identity? And 1, 2, 3, 4, 5 appear already, right? Okay, so we don't want this. Who else haven't appeared? Who else haven't appeared? Which combination haven't appeared yet? Wait, 1, 3, 2, 4, 5 haven't appeared. Okay, 1, 3, 2, 4, 5 haven't appeared. Okay. And then, do you have identity? How to get identity? 真诚. How to get identity? 1, 3, 2 times 1, 2, 3. Good. First time I hear your voice. Good. Okay, so yeah. So check that this is a cyclic group. Okay, so this is a cyclic group. Check that this is a cyclic group. Okay, see if you can define an isomorphism or not. Okay, define it. Yeah. Practice this defining these isomorphism is a good exercise. But what do you note here? This is a permutation of how many elements? 5. Okay, but just now I said this is a subgroup of X6. Okay, so meaning what? Meaning you can actually find the subgroup in a smaller Sn. Okay, which is a subgroup of X6. Okay, so Cayley's theorem just gives you the subgroup in S of cardinality of G. Okay, but the subgroup, the image of G you have might lies in a smaller Sn. Okay, might lie is a smaller Sn. Okay. Okay. So see, S5 is a subgroup of X6. How many ways S5 can sit in X6? You know? You can either permute 1, 2, 3, 4, 5, or you can permute 2, 3, 4, 5, 6, or you can permute 2, 3, 4, 5, 6 through 1, 2, 4, 5, 6, 1, 2, 3, 5, 6, 1, 2, 3, 4, 6. Okay, so there are 6 ways for x5 to sit in x6. Okay, yeah. So what I do in my research is to look at all these ways sitting inside the Sn. Smaller Sn live in a bigger Sn. Yeah, and then we try to use string to draw it out. Yeah, we try to use string to draw it out. Okay. And then what should we do next? Okay, let's continue for a few more, and then we will discuss assignment. Okay. Yeah, just now 3 comes to me, right? So we have a left. Can we define a right or not? Okay. The answer is you can define a right regulation, and the whole proof also hold by using the right regular representation. So imagine what you do if you multiply on the right correspond to the multiplicative table. If you multiply on the right on all elements, what do you get? Just now you get row, now you get column. Okay, you compare columns. Okay, so it's also a good exercise if you can repeat the whole proof using a right regular representation. So x to sg instead of, so s to gx instead of x to sg. Okay. Okay, let's go into a definition first and then maybe prove one proposition before we jump to assignment. So next definition is called the coset. Coset. Okay. So what's the coset? So you need to first take a subgroup inside of G, okay, and then take any other element in your G, okay. Then the subset of AH is called all the elements A times H for H in H is called a left coset. So let me ask you a question. Is this a subgroup or not? This is a subset of G, right? But is this a subgroup? Is this a subgroup? Huh? Is this a subgroup or not? Or should I ask, is this always a subgroup or not? Thingy, what do you think? Yes, it's a subgroup. No, it's not a subgroup. Okay. So in general, a coset is not a subgroup. Okay, in general. So why is it not a subgroup? Inside H, there's an identity element. Okay. So if you take any element in G, which is not identity, okay, and then it's not an inverse of anything in H, so how do you get back the identity? There's no way for you to get back the identity. Okay, so you need to check, just check some property, some obvious property, okay, to verify this. Okay, so you just need to check whether identity is always in my coset or not. Okay, it is not always in my coset. Okay, so this example, there's an example here. So what's the coset? So H is always a coset. Why H is always a coset? Why? Why is it always a coset? Or left coset? Why? Definition. What's the definition? Does it satisfy this form or not? A times H. How? How to satisfy? How to satisfy? Huh? Is H of a group Is a subgroup always a coset or not? H equals to what? E times H. Okay. In particular, E is in the group. Okay. So H is always a left coset. Okay. So let's look at a closer example. Look at Z6, for example. Okay. So Z6. Yeah, okay. So what's the subgroup here I'm interested in? So let's take our H to be the trivial group. Okay. Let's look at this example and then maybe we could stop here. I mean, for the lecture part. So let's look at this subgroup. This is what kind of subgroup? It's a trivial subgroup. Okay. So what kind of concept I can make up from this subgroup here? Trivial subgroup. What kind of concept I can make up here? What are the other elements in my? What are the other elements in my? 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. So, what do I do? So this is a subgroup, right? Okay. So this is a trivial subgroup in particular. So this is a trivial subgroup. So what can I do next? I can look at the coset 1 times. Okay, in this case, it's not times, right? In this our case here, last time we write plus bar. The other coset I have is 1. Okay. How about any more? How many coset do I have? Seng, do I have any more coset or not? No more. What are the elements in Z6? Element in Z6. Okay. 0, 1, 2, 3, 4. That's all. 5. Okay. So how many coset I can build? 5. Okay. 6 if including the trivial subgroup or including the group. Okay. So 5 of them. So the other 5 are 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5 plus a subgroup. Okay. So you have 1, 2, 3, 4, 5, 6. 6 coset. Okay. Coset correspond to the subgroup, trivial subgroup. Okay. So there are, so let me write down. So there are 5. Okay, so there are 6. So there are 6 coset, including H itself. Okay, including H. So there are 6 coset. Okay. Yeah. Any question or not? Question? Yeah. For any trivial subgroup is a trivial. Yeah. Yeah. So I mean this H here, there's no any other condition. Okay. Yeah, you can take trivial subgroup as your subgroup. And then you build coset. Then you start with a subgroup and then you build the coset. Okay. So in particular, actually in this example here, right? Okay, if you remember from your discrete math or number theory, so these 16 partition your set. Okay, in this case here, partition your group. Okay, so later on, we'll prove that left coset will partition our group. Okay, in general. Okay. In particular, partition relates to equivalence relation. Okay, so this means left coset define a equivalence relation. You can prove that like left coset is a equivalence relation. Okay, maybe we won't do it now. Okay, we'll do it later. And then what else I want to say? So similarly, you can define a, if I have left, surely we have right. Again, left and right. So you can define what is HA. Okay, A times everything in the set. Okay. Yeah, so maybe I'll stop at the definition of coset for the lecture today. Any question or not? No? If not, then we quickly jump to assignment. Okay. For the assignment, I've looked at it. For those who already taken my class, know my pattern. So you need to answer question with, okay, with understanding, sure. And then your solution must provide explanation. Okay, don't just put equal, and so on. Okay, so how deep you need to explain. Okay, at least what we taught here, you need to write it up. Okay, I mean, what is tested in this course, you need to write it up. Okay, if you assume some linear algebra knowledge or calculus knowledge, those you can just stack them, no need to prove them. Okay. Yeah, so what do I mean by that? Let's look at some example, okay? So first question is prove that the multi-matrix multiplication for n by n real matrix is associative, okay? So what's this question asking? So this question is testing about LOC, okay? Associative LOC. Please check your own solution and then also compare to my solution. Try and learn, okay? The way I wrote, the way you wrote, okay? And then compare. See how you can write better. So in this question here, one thing I want you to learn is the matrix multiplication notation, okay? You should recall that from your linear algebra. And then distributivity of real numbers, associativity of real numbers, okay? And then finite sum commute. You don't need to produce the proof for me, but if you don't understand why finite sum commute, you should prove it. Okay? And some of you use Fubini's, it's not necessary, okay? Fubini's is about summation plus limit, okay? And then infinite sum. So that one too overkill already, okay? Okay, and then let's go first. So next part, this part prove that left identity and right identity must agree. Most of you got it for this part, but I'm a bit uneasy when I see this. Quite a few of you write this down. What does it mean? This means that E1 times E2 equals to E1. E1 equals to E2. But I asked you to prove E1 equals to E2. So how can you write this down? So what's the order you get? What's the order you get? You should get E1. You should get E1 times E2 equals to E1 first, and then E1 times E2 equals to E2, and then only equal on this side. So why is it equal on this side? Because E1 times E2 is the same. Okay, so the order is like work like this. Okay, E1 equals to E1 times E2 equals to E2. Okay, so please make your order right. Okay, this is what you want to show, and then you tell me this is true. Okay, and then also what's worse, I already showed this in class, you know. I already showed this in class. Why you guys don't just look at the slide and read the slide? Why is it so hard for you to read the slide? Okay, question 3. Suppose that G is a set with associative LLC and has an identity. Okay, prove that if delta square is invertible, then delta is invertible. Okay. Most problem arise when you want to prove delta 1 exists, but you are actually using delta inverse already. Okay. What do I mean by that? So we know that delta square is invertible. Okay, delta square is invertible. Then you simply just break this into delta inverse times delta inverse. How can you do that? You haven't proved that delta inverse exists yet. And then you haven't shown that this is actually equal. Okay, you cannot simply split, okay? Don't take equation for granted. Okay, so this is your problem of just learning maths using examples. You don't know what's going on. You just copy, paste, maybe change a few numbers. Okay, this shouldn't be what you are doing in mathematics degree. Maybe it's suitable to go accounting or what. Okay, you need to constantly ask why you want to do this, why we have to do this. Okay, that's why I don't like to give you those repetitive exercise because it's useless. You learn nothing. You don't know what you are computing. Okay. Yeah, so you cannot assume delta inverse exists and then you use cancellation law on delta inverse. Cannot. And don't assume things that haven't been proven yet. Part 4. Generally, people did quite good in part 4, question 4. Yeah. And I already mentioned a little bit of hint in class as well. The important thing for this question is to address associativity. Okay, is to address associativity. And then question 5. Prove that the intersection of two subgroups is a subgroup of G. Prove that the union of two subgroups of G is not a subgroup of G unless one is contained in the other. Surprisingly, part 2 done quite well, but I have some comment on part 1. Can I have a raise of hand how many people show that something is a subgroup using AB inverse is found in H? Can I see how many of you? How many of you show that AB inverse is in H for all AB? Can I see? How many of you? Hello? And you don't know what you are doing, is it? And can I see a raise of hand? How many of you use AB inverse is in H? Can I see? How many of you use AB inverse in H? 谁 show that inverse intersection is a subgroup 用 AB inverse 是谁？我没有要骂你，我只看一下多少人罢了。你要 be honest a bit， 诚实一点好吗？AB inverse。你们的 solution 是在我手上，你知道吗？不需要我一个一个教，可以诚实一点吗？华语也听不懂，英语也听不懂。谁说的 AB inverse 是在 subgroup 里面？我可以跟你们讲，你们这样是很难沟通下去。我跟你们讲， Now, everyone, look at your assignment, question 5. Look at your own solution. Who show that it's a subgroup if AB inverse in H? In the intersection.你不要我点名啊，没有要骂你，但是请诚实一点好吗？还是你连你自己在做什么都不懂？那你做人真的是很可悲啊！OK， 我现在念出来啊，我念出来这句话是谁在跟我承认？我没有要骂你，我只是要问谁做这件事情吧。Therefore, in both K1 and K2, such that AB inverse 在里面 in there, so AB inverse is in the intersection of K1 and K2. 谁写的 ？Who wrote this? 你不承认，我要念名字哦。Who used K1 and K2 notation in this question? 雪梅，你不知道你在写什么？你答案从哪里来？啊？你没有写 ？OK， 好，非常谢谢你。我没有讲 in H， 我是说 in 那个 intersection。OK。Who wrote this kind of argument? I ask again. Other than Xie Mei, who else write this kind of argument? Okay, Ling Jing, very good. Who else? There's two? I don't think there's only two. Who else? Just two. Okay. Anything wrong with the argument or not? Is anything wrong with those arguments? Let me ask you, how you get this answer? Where do you get this answer? Huh? Good. You know why is it true? Google said it's true. We never introduce subgroup like this. How do we introduce subgroup? Closure, identity, inverse. Okay. So actually, this is a proposition. H is a subgroup of G if and only if for all AB, AB inverse is in H. Okay, so this is a proposition, need to be proven. We didn't prove this in class. You cannot use. If you want to use, please prove it. 明白吗，林静？ Yeah, 明修。What's the difference? You need to submit all. Cannot. Only the result proven by me you can use. So that's why I say my lecture note is very important. If my lecture note didn't cover anything, you cannot use. So if the more things you discover, then the more things you can use. Okay. So the practice in mathematics class is you cannot use stuff other than what you have been given. okay, in the lecture. And a lot of you show an extra condition, which is associativity. Why do you want to do that? Why do you want to do extra stuff? I thought you say you have no time. Why you want to do extra stuff? The purpose of doing question 4 is to reduce your job, but you increase your job workload again. You just need to check 3 properties: closure, identity, and inverse. You don't need to show associativity. Why? 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 It is a subset of H. Okay, so it's induced operation. This is exactly what question 4 is telling you. I purposely ask you to do question 4 so that you don't need to check associativity. And then you go and do question 5, check associativity again. Why like that? This means what? You don't understand what I'm giving you to do. You don't understand what you are doing. We spend so hard time to prove question 4, saying that associativity is not important. This is what question 4 is telling you, not important. And then when I ask you to prove subgroup, then you go and show associativity again. Don't waste time. Of course, if you want to do practice yourself, can, but you don't need to write into your solution. Okay, okay or not? Please understand what the question is asking. Okay, question 6. Okay, question 6. I cannot say easy or hard because there's some of you still don't know how to break sum into this cycle here. Okay, break permutation into product of transposition. And then some of you confused with the example I gave in lecture. You thought that it's just swapping rows. Actually, it's not. Okay. What does this matrix have to satisfy? It has to satisfy the matrix vector multiplication. Okay. So meaning if I sense 1 to 2 here, I must make sure that when I apply the matrix to E1, I get the matrix E2. Okay. If you think of it as swapping rows, what you do is actually you are doing row matrix multiplication. Okay, this is what you do. This is a different convention. Okay, so these two, oh, sorry. Yeah. So these are the 2 conventions you have if you have your P sigma with row swap. Okay. Okay. Yeah. So let me see. So about 3 of you is in a dangerous zone. Okay. What do I mean by dangerous zone? And then those people are not here. Please tell them you are in dangerous zone if you are below 20 and a neighborhood around 20. Okay. Plus some epsilon around 20, you are dangerous. And 20 plus some epsilon. And we got 4 high scorer here, full score. We got Sun Ling, we got Jing Bo, we got Wen Suo, and we got Yu Wei. Okay. So if you need help, maybe you can check them out. Okay. And then I want to praise Yuan Jia this time. Okay. Because in calculus 2, I don't know what she is doing. Okay. But this year, this this semester, I read her assignment. I feel like she should do well. Okay. You should do well. Okay. Please keep it up. Okay. So please understand what's the question asking. If you don't understand, why not look for me? There are 2 weeks time for you. Okay. If your friends doesn't want to help you, can't find me. Okay. And I'm in my office hour. Only Jingbo come every day, every week. Right. So have you done the tutorial question or not? No. Very honest. Please do. And already people do it for you. You don't want to read. Did you read? Did you read Jingbo's solution? Read, also don't want to read. How can I help you? Yeah. So last time I told you about a person, right? Go from 29 to 22. It's in your class. And that person, I will tell you who is he. He's actually, Shen, who is your friend? Yongzi. He's Yongzi. And actually, I feel quite sad. Why he failed LA shouldn't be. If he can perform well in calculus, why LA can fail? Yeah, so please put some heart into study, okay? I know you want to enjoy life. Please put sometimes, okay? Sometimes, at least. Okay? If Yuan Jia can do it, why can't you? If Yongzi can do it, why can't you? Yuan Jia, tell them how you change this semester. What you did? You did. Just now you tell me one. Tell them. Have a healthy life. What do you mean by have a healthy life? Huh? Sorry? Schedule your day. What do you mean by schedule your day? Yes.